Good afternoon and welcome to track 2. For the next hour, I will provide you some information regarding security issues in two widely used protocols, Multicast DNS and Dnsrf Discovery. So the objectives of this presentation, of this talk, is actually, first of all, to provide a kind of complete threat analysis to the best possible extent of these two protocols. I will explain you later what do I mean by this complete analysis. Secondly, to give you some information regarding an open source tool that I have authored and is being released. And this tool was written in order to support this study. So when I was finding out an issue in these protocols, I was trying to implement it in a tool in order to test it. Third, of course, to perform some experiments, at least in this case, to present you the results of them. And finally, to discuss some potential mitigations. The methodology that I used for the threat analysis was, let's say, pretty straightforward, I would say. I took the RFCs. Everything is specified there in detail. Every single piece of the RFCs was examined piece by piece. And potential issues were identified there, either because of some ambiguity in the RFCs or potential, let's say, topics where misimplementation of the vendors would be expected. Of course, as I said, in order to test all of them, a special tool was crafted. Before we move on, let's refresh our knowledge regarding these two protocols. Let's see what they do and how they are used. First of all, both of these two protocols are part of the family of the protocols used for the so-called zero configuration networking. The concept is really simple and convenient. I want to take my laptop, my smartphone, any kind of device, go somewhere without having to configure anything to be able to operate the network directly. This zero conf requires three things. A kind of automatic app configuration. When it's automatic, we don't mean a DHCP address, but something similar to the, let's say, stateless address auto-configuration of IPv6, for instance. Then we have to provide some kind of hostname resolution, even if a DNS server is not there. And of course, to provide some service for discovering potential services required by our host. Both protocols are used already by many devices like Apple TV, Chromecast, home speakers, NAS devices, and so on and so forth. In a nutshell, MDNS, which is defined in RFC 6762, provides the ability to perform DNS-like operations, but on the local link. For this purpose, it uses UDP, of course, but instead of the typical 53 port of the Unicast DNS, it uses port 5353. On the other hand, Dns Service Discovery, defined in RFC 6763, as you can notice from these numbers, they go hand by hand, allows clients to discover instances of a desired service in a specific domain using standard DNS queries. For instance, you are in a network and you're looking to find out a web server, something that offers HTTP services. We run DNSSD to provide us with a potential instances of web services run over the network. However, there is a small difference between DNSSD and Multicast DNS. While Multicast DNS was designed for the local link only, DNS Service Discovery can be used, and it is used, both on the local link over Multicast DNS or using, let's say, typical Unicast DNS queries. A few more details about Multicast DNS. First of all, a specific top-level domain has been defined, the .local top-level domain, which, according to the RFC, has local significance only. So it can be used only on the local link again. Moreover, it is described that Multicast DNS can potentially be used for typical, let's say, DNS resolutions, as long as there is no conventional DNS server on the network, but this feature should be disabled by default. It uses this specific IP multicast addresses. It allows unicast operation, although it's a multicast protocol, it allows unicast operation, and this is a key issue here, but it defines that this unicast operation should be used on the local link only. Finally, except from the multicast addresses that I mentioned above, there are some specific link local addresses used for reverse mapping. So if you have a name, since we want to perform host resolution using multicast DNS, there are this link local reverse mapping which can be used in order to provide name resolution on the local link. Finally, another key issue here is that given that multicast DNS is a protocol designed for the local network, there is a kind of measure which is taken. And this is also the case for every kind of protocols which have only local significance. And this measure is that the TTL value should be set to 255. When I use the words should, may, must, etc., I follow the terminology defined in the RFCs. So should is not a typical English word should, but it actually means that you should do this, or actually you have to do this more or less, unless you have a really good reason not to do this, and as long as, again, you know all the potential implications. So given that the maximum value of the TTL in the IP field is 255, this value should be set to 255, the maximum one. So when you receive a packet and the value of the IP TTL is less than 255, you can realize that this packet has come outside of your router. So it has gone at least through one hop. This is a measure used even network discovery messages in IPv6, for instance. The weird thing here, though, is that although the RFC defines that this should be the value used in MDNS packets, it doesn't restrict or it doesn't advise to discard them in case this is not the case. So host has to use this value, but if they receive a packet which does not have this value, they do not have to discard it. They must accept and process it. A few words about Dnsrf Discovery. The syntax of this DNS messages is, or names actually, is presented on the slide. So if we look, for instance, for a HTTP service, we use this kind of DNS name to query. Usually the domain field here is the .local when used on the local link. So if we query for HTTP services, we will get answers regarding all the instances of potential HTTP services on the network. Now, when we get these instances, when you know which kind of HTTP services are supported, we can go one step further and query these instances and get some extra information provided through SRV and TXT records. So what's the problem with these protocols? These protocols, and especially multicast DNS, is based on a basic and fundamental assumption. And it is clearly defined in the RFC. The assumption is that there is a cooperating participants environment, that none of the participants shall misbehave. The problem is that maybe this assumption could be valid about, let's say, 10 years ago. I believe that nowadays it's not necessarily the case, especially since we live in the Internet of Things and the bring your own device era. So go somewhere in an airport, in a cafe, even in a hotel like this one, and connect to the network. But I don't think that we can assume that this environment, for instance, is a cooperating participants environment. The second problem is that due to the protocol used, the UTP protocol, which is spoofable, this is not new, of course, but this is not combined with a kind of validation mechanism for someone's persona. If we don't have any way to confirm that the host who is trying to talk to us is indeed this host and not something else. And another problem is that although these two protocols, and especially multicast DNS, has been designed to be used on the local link only, so it should be restricted on the local link, this is not necessarily the case for whatever reason. Now, there has been some related work. The oldest blog post that I found out was back in 2008, which described the type of information that you can retrieve from this kind of messages. Some similar work was presented more recently in 2012. And just 1 year ago, there was a very thorough study of this protocol, but only from the perspective of potential man-in-the-middle attacks. This is a very brief list of my lab, let's say, what I tried to test during this work, the devices. And this is the categories of the attacks, the types of the attacks that I identified. Reconnaissance, we always start from there. Some spoofing at man-in-the-middle attacks, denial of service flooding attacks, remote unicast interaction, and the implications, of course. And finally, we'll examine some other potential attack vectors, not necessarily on this order. Reconnaissance, it's always the first step. So, normally, a laptop or a device like mine, for instance, if it wants to access a service, it doesn't ask what kind of services are available. It just asks if there is this specific service available around. So if I'm looking for a printer, my laptop will try to identify a printer. However, in the RFC is defined that there is a specific query which can be sent to this service name, which has been defined just for troubleshooting purposes. It doesn't serve any purpose on the real operation. So if you send a query on this service name, very conveniently, you get all the types of services which are available on your domain. And this is just an example. For instance, you can see clearly here, I believe, that we have some kind of HTTP service available. We have SSH, we have SMB, some other as well. And we even have this kind of workstation service. A few more words about the workstation service. While all of the other are related with pure services provided from servers, the workstation service, named as kind of workgroup manager, as described in the manual pages of Avahe daemon, it is useful for administrative purposes, and even, I would say, worse. In some cases, in some operating systems, it is enabled by default. So even if a laptop, for instance, does not provide any service like HTTP or SMB or whatever, it may have this service available, which makes it, let's say, identifiable in the network. Now, first, we get the types of the services which are available. The second step is to identify the instances of each specific type of service which are available. And with them, we also get this SRV and TXT records which provide more information. This is the output of a query, which queries the SMB service. If you recall in the previous slide, I showed the generic query where we identified all the types of services. So SMB was one of them, and now query the SMB service. And to get these answers, from the name you can figure out that it is probably a NAS device, at least it is named like this one. And some extra information here. This is the same for the SSH service that it was also available. Here you can see, for instance, that despite I have queried the IPv4 network, very conveniently I have gotten here even the IPv6 address, which is available. And of course, we have the port number and the operating system. Okay, we typically expect SSH to be on port 22, but it's always convenient to have it confirmed. Some more information, we had an NAS before. So, by querying it further, we can see that we have the vendor, Synology, model, blah, blah, something, serial number, and some extra information like a major release, minor release, the build number, admin port, secure admin port, etc., etc. So a lot of information just in a few packets without having to scan our network. Another query for another system. This is a response to the workstation service that I mentioned before. Again, very conveniently, we get the information that this is a Linux system using a 64-bit architecture. And the final one, this is my home speakers actually at home. I was really surprised when I saw that they used Multicast Dns. So we have, okay, the description, home speakers, the model, the brand name, etc. And I even found out that they use Linux over an ARM v7 processor. So we have 3 steps in order to perform our reconnaissance using Multicast DNS. I have tried to combine all of them in one switch in the tool. So using just this switch, you can run all these 3 tests in one. So the first step is to query this specialized service name, which has been defined just for troubleshooting purposes. We get the types of services, then we query these ones. We get the instances of the types of services. We query these ones, and we get all the other info. A 3-step approach which provides all the information available on the network. And the best part of it, of course, it is all this is multicast on the local link, so we can spoof our source address without being identified. Now, in the beginning, I also mentioned that multicast DNS and DNSSD is also used for DNS reverse mapping, at least on the local link. And this is a typical packet where you can see that both for IPv4 and IPv6, we have this kind of reverse DNS mapping. So if we want to scan a network and if we want to identify which IP addresses are available, instead of performing a kind of sweep scan, as we usually do, we can very simply send one multicast DNS packet, which will query all these DNS reverse mapping addresses. This is a typical class C network. And the packet will look like this one. Eventually, it's not just a packet, it's a combination of packets because the packet has to be fragmented. It's one datagram, but given that we have added too many addresses and too many reverse mapping, let's say, requests, this datagram has to be fragmented. But it is, for the recipient, it's just one datagram. Now, after finishing the reconnaissance, we will talk briefly about the man-in-the-middle attacks. I'm not going to spend too much time on this, just because it has been examined thoroughly in previous work. Just to provide you some examples, how to construct specific, let's say, multicast DNS or DNSSD packets using the tool. As an example, I'm using a packet with 1 answer and 2 additional records. And this is a command. It seems complicated, but if you get the logic behind this, it's not complicated at all. I mean that you have to use, let's say, a backslash as a kind of delimiter between the different fields, and then provide the typical fields so that you can find in a multicast DNS or a DNSSD packet like TTL, where the flash bit should be set or not, what should be the target, if this additional record or not, and so on. And this is how this packet would look like if you use the previous command. Similar examples here, TXT record, SRV record, service record. So you define the type equals to SRV, and then some specific fields which can be found in these records, like the port number, the weight, and the priority of the records. And an example using TXT. However, because I'm a bit a lazy guy, when I was running all these tests, instead of having to, let's say, manually craft all these spoofed responses, I tried to automate them. So I have implemented some functionality where, in case there's some kind of request for a specific service, then this tool automatically responds and pretends that it offers the service. And I have implemented this specifically for the Workstation Service, printers, Unicast, and AirPlay. Of course, some generic responses are also provided, but when I have found out when you specify in detail what the response should be, it is more effective. Now, I must clarify that in order to perform multicast man-in-the-middle attack, providing a fake DNS advertisement is only, of course, the first step. In order to perform a successful man-in-the-middle attack, you have to, of course, implement a specific service. So if you pretend that you are a printer, except from advertising that you are a printer, you have also to implement the printer functionality. If you pretend that you are an AirPlay TV, except from advertising this, you have also to implement this functionality in order to have some clients connect on you. Moreover, in some cases, there are some kind of obstacles, I would say. Some asymmetric key verification is used. I will talk to you about this later. Or some devices like Chromecast, for instance, no matter what, they ask to connect to the internet. I mean that you cannot have this kind of devices on a kind of isolated network and, let's say, emulate them. Talking about asymmetric key verification, in the past it was identified that Apple TV and iTunes use a kind of asymmetric key validation. So iTunes could use this verification in order to validate that the device that they are talking to is an Apple TV device indeed. However, this keys, the corresponding private and public keys were extracted. And as long as you have them, then the attack again falls back to the typical, let's say, man-in-the-middle attack. Some parameters that you can use with the tool in order to spoof your messages, like to spoof the source address, the IPv4 address, the IPv6 address, to randomize your MAC, or to spoof your MAC address, etc. And some tips for these attacks, because eventually it's a kind of a race condition. I mean that if there is some legitimate device on the network, you have to win this race. So in order to do so, first of all, it helps if you set the priority or the weight of your survey records in a higher priority. There is also the so-called cache flash bit, which when it's set, it tells the host that they should override their existing cache value with the new information that they just received. So you put the highest priority here, the highest weight, and at the same time you tell the host that this is the new value, delete what you have up to now and use this one. A few things about the size now. In theory, a multicast DNS packet does not have to be very long enough. Very rarely has to be more than the MDU size. Nevertheless, the RFC allows the fragmentation of these packets. Now, in practice, it tries to put a kind of limitation on the maximum size of these packets, and this is about 9,000 bytes. And if you notice here, they use a quite strict language for the RFC terminology. Must not exceed, which is much more strict than the typical should not exceed. So any kind of multicast DNS packet should not be more than 9,000 bytes. In practice, what I have found out is that actually there is no limit. Vendors, they do not implement this check, and even let's say a 59,000 bytes packet can be sent. So eventually your datagram can be as large as a typical IP packet can be. What does this mean? Very simple, that there is a lot of room for data exfiltration, for fuzzing, or even some room for command and control operations, for botnets, etc. Provided that, of course, this is used with a kind of unicast operation. TXT records, more or less similar case. I mean that if the maximum size of a multicast DNS packet is 9,000 bytes, then in RFC it's defined that the maximum size of the TXT record should be 8,900 bytes. But again, the tests have shown that actually this limit is not enforced from the vendors. This is just two examples which shows how you can use the tool to craft very long TXT messages. This is one big TXT record using some Python here. And this is a huge TXT, one huge MDNS record incorporating many different TXT fields. Now, if there is a room for unicast DNS cache poisoning, if you recall, we said that in theory, multicast DNS can be used for conventional DNS name resolution, as long as, of course, there is no typical DNS server on the network. But this should be disabled by default. Thankfully, in this case, it is one of the cases that the vendors implement strictly this specification and did not allow any kind of, let's say, DNS cache poisoning. just some fields that can be used with a tool. And now let's go to the more interesting part, I would say. First of all, some DOS challenges that we may have. In order to perform DNS, we have, as you could see, we have several options. The first option is very simple. We can simply set the TTL equals to 0. The TTL here is not the IP TTL that I mentioned at the beginning, it's the DNS TTL. So when you set the time to value equal to 0, we simply say that this DNS name is no longer valid, and you have to delete it. So you can easily identify what kind of DNS services are available in the network, which ones have been advertised, and then spoof this kind of messages by setting the TTL equals to 0. And the recipients, the host, will simply delete these records, and so you implicitly perform a kind of DOS to this specific service. I have used this method and it works really well, even again, let's say commercial devices. But of course, again, it's a kind of race condition. I mean that you have to send again and maybe again this kind of TTL equals to 0 messages. Again, some examples how to use them with the tool. You must always ensure that you spoof properly the source IP address. Another very interesting operation of multicast DNS is the so-called probing. So when a host starts up, or after a reboot, for instance, and it wants to use some kind of services and to correspond the services to a specific service name, given that this is a kind of, let's say, peer-to-peer communication, it has to confirm that the specific names are not used by any other host in this network. So it performs a so-called probing. So, for instance, it sends queries asking for this specific service names. If my laptop uses the name MyLinux, it sends a query to see if the MyLinux service name is used by someone else in the network. If it receives no answer for a specified amount of time, then it knows that it is available and it can use this name. Now, the problem starts when it receives a response and someone else, another laptop, let's say, claims that the MyLinux name is already used from another machine. In this case, it simply changes the name and it uses, let's say, MyLinux 1. And if there is again a kind of conflict, MyLinux 2, and so on and so forth. Of course, in a real situation, in a legitimate environment, at some point, this resolution, this conflict will be resolved and this will be over. So you will find out that the name, let's say, MyLinux 25 is not used and it will use it. But this is not always the case. The RFC says that if there is a conflict for a long period of time, then at some point the service should stop and should give up and should let it identify the application that tries to use the service. What I found out is that I tried to trigger this response automatically. So when there is a request for a service like MyLinux, I was responding that MyLinux, I use it. MyLinux 1, I use MyLinux 1. MyLinux 2, I use MyLinux 2, and so on and so forth. And I found out that instead of stopping all this process at some point, actually this process never ends. And it continues for an hour, for 2 hours, and so on. Well, the results are pretty obvious. First, there's a lot of flooding in the network. And secondly, eventually this service cannot be used from this under attack, let's say, host. And this is just an example how to use the tool in order to reproduce this kind of attack. I set a timeout here just because I wanted to stop it after an hour because it actually never ends. Some other DOS capabilities. You can even use negative DNS records in order to say that this DNS record does not exist, so delete it. Or you can cause the so-called MDNS suppression to tell the legitimate host that I already advertised your service, so you don't have to do it. and so you suppress it, and the other hosts are not aware of this service. Of course, all this can be combined with the flooding of the network. And in some cases, depending on the operating system, of course, and then on the message that you are crafting, you can achieve an amplification factor of even up to 8 times the traffic that you send. 8 times the traffic that you produce is amplified on the network. Now, probably the most important case regarding multicast DNS is the potential remote unicast interaction. All these attacks that are described so far are mainly applicable on the local link, unless, of course, we find a way to remotely interact with the service. Officially, as I had said, multicast DNS can be used or should be used only on the local link. However, there is a provision for a unicast operation. If you recall, in the beginning, I mentioned this TTL case where, although the TTL should be 255, there is no restriction regarding the discard of these packets. In order to ensure that these packets do not come outside of the local link, there is a provision in the RFC saying that the recipient more or less should check whether the source address of this packet is a local link one. So if my host has a specific, let's say, IP address, it checks if the sender of this packet belongs to my local IP network. For instance, in case of IPv6, if this is a local link IPv6 address. So eventually, this is the only countermeasure used in order to prevent remote unicast operation. And when I say remote, I mean outside of the local link. The question is, what could be the issues if an off-link unicast query is accepted? Well, first of all the reconnaissance attacks that we described so far can be used remotely, which is even more convenient and useful, of course. All these DOS attacks can also be launched remotely, again, as long as this remote unicast operation is permitted. And sometimes you may even have even a major issue. You can imagine that if an attacker knows that this host, let's say, interact to a unicast MDNS operation, if an attacker spoofs the source address of the target here, given that this is a spoofable protocol, all the hosts will respond an amplified response to the target, and so you will have a kind of distributed denial of service attack. And this was actually the case described in this vulnerability released in 2015, where it was found out that for some specific devices and some specific implementations, they allow interaction remotely, and so all this, let's say, threats like information gathering, etc., specifically DDoS, could be applied remotely. And this was the list at that time of the systems that were affected or not. But all this belonged in the past. I mean that most of the vendors have patched their systems, so the situation seems to be okay. However, there is always a however. Okay, some modern operating systems have been patched and they are not vulnerable anymore to this. But some embedded devices, like the home speakers that I mentioned at the beginning of the presentation, still use this kind of, let's say, vulnerable versions of MDNS. And I'm not talking about here about old speakers. I mean, the speakers which were bought, let's say, 2 or 3 or 5 years ago, but I'm talking about speakers which were bought, let's say, 3 months ago. And the question is, how often this can happen in the real world, in the network? How possible is to have this kind of attack? If we run a query to the well-known Shodan search engine, you will find out that about more than 900,000 devices seem to have opened the UTP port 5353. To be honest, when I saw this number, I was a bit surprised because typically I expect that this port is blocked remotely or should be blocked remotely. Nevertheless, this does not necessarily mean that all these numbers, all these devices are vulnerable. It doesn't mean that we have 900,000 devices over there which can be triggered for a DDoS attack. However, I believe that the chances are really good to identify a lot of them over there that potentially could be abused for this purpose. But again, this is a kind of devices that have not been updated or do not follow, let's say, the trends of operating systems. Another problem is the following. I'm sure that most of you remember the so-called ping of death, which was released, which was back in 1990 something, I don't recall, where you could, let's say, DOS a Windows system just by crafting a very, very large IPv4 packet and bigger than the maximum allowed datagram. So this was back in 1997, and in 2003, it reappeared over IPv6, the ping of death. Same problem, different protocol. Similar case, in 1998, there was a thorough paper describing all the potential attacks that you could launch by using fragmentation, overlapping, and all this stuff. In IPv6, at this time, they tried to be smart, and so they defined an RFC. In 2009, still 11 years later, trying to solve it. But in 2012, the problem was still there. So as you can see, the problem reappears. So I guess that you can imagine now what's happening now in this case. All this problem with the IPv4 and the Multicast DNS, which can be triggered remotely and which has been patched, at least to some extent nowadays, it reappears in IPv6. So systems which are not vulnerable over IPv4 were found out to be vulnerable over IPv6. So if you do have your IPv6, their IPv6 addresses, you can still use them in order to interact with them remotely and launch any kind of the attacks that we described in the beginning. A kind of hint here, in order to force a unicast response, because it is not only to send a unicast query and this query to be accepted, but you also want the response to be a unicast one, you must set this qubit to your response. Again, some switches that you could use with a tool in order to reproduce all these kind of attacks. So, and now what? We described several attacks, starting from reconnaissance and DOS, DDoS, etc., remote unicast. What can we do in order to prevent all these, let's say, problems in our networks? The most typical one, it's always useful. It may seem very, very obvious, but as we saw, it's not that obvious eventually, since we have found out about 900,000 devices over there. Block this port number, not only for incoming, but also for outgoing messages. Your host have no reason, not only not to accept them, but not even to send any kind of these messages remotely. Secondly, of course, control your device. I mean that I'm not sure eventually how many of us really use or need this multicast DNS protocol. If you don't, just uninstall it. But this is some measure just for as a first aid, I would say. Some more permanent fixes. I believe that the RFC should change. I'm going to propose some specific measures for each one type of the attacks. So in order to have an extra measure for this remote unicast operation, I believe that the RFC should force the discard of the packets when the TTL of the received packets is smaller than 255. There is absolutely no reason to allow packets with a smaller TTL value in your network, at least regarding multicast DNS messages. It's an easy way to control this. Secondly, okay, multicast DNS and Dnsrf Discovery have been specified in order to provide this zero configuration working capability, which is really convenient, of course. But this does not mean that there should not be any kind of validation of someone's persona. So typical, let's say, or an easy solution could be the establishment of a kind of a trusted PKI relationship, where if you use a device like Apple TV or a Chromecast or whatever, this to have a valid certificate, which has been signed, of course, by a valid CA, etc., etc., and your application, in order to access and use this device, will have to validate the certificate using, again, the typical procedure. So at least you will know that if you are talking to someone and it pretends to be a printer, it is a printer indeed. And finally, in order to resolve some issues regarding these conflicts that I mentioned, where you could pretend that you already use or claim that you own the service name, there are solutions over there which are used by other protocols, like the Back to My Mac protocol, where you can define some kind of unique host identifiers. As an example here, I use the so-called IPv6 unique local addresses, where a globally unique identifier is established on its host based on a pre-specified, let's say, algorithm, part of which is also the MAC address of the device. So if you construct a completely randomized identifier and someone pretends that it already owns this identifier, then you can be pretty sure that something is going wrong, and this is not really the case, but someone is trying to deceive you. Conclusions. ZeroConf is useful indeed. It's really convenient to go somewhere and just plug and play everything. But in my opinion, the risk operating participants environment cannot be guaranteed anymore in nowadays. So there should be a kind of automated trust establishment mechanism in order to ensure that we know that we are talking to a specific person where we are referring. And the obvious things, as always, never forget to control your perimeter as needed. If you want more information, the tool is available on this link. As I said, it's an open source one. You can use it, change, etc. And there is also a white paper where you can find all these attacks in more detail and some even more stuff. And finally, these are the references that I used during my presentation. Questions?
Hi. You propose as a mitigation to use is it signing using certificates?
Mm-hmm.
And devices should get a certificate that is signed by a trusted PKI CA. At the moment, I think you basically only sign for specific domain names. And in this case, you're actually more interested in a device being an actual printer, for example. So suppose I could get a StartCom certificate for my MDNS device. StartCom doesn't deliver printers, but how's the device or how's the application supposed to know that?
Okay. The major vendors, except when they manufacture a device, they also own some specific, let's say, domain names. For instance, Apple already has established a kind of subdomain for the, nowadays it's for the iCloud. It used to be for the, I don't recall the exact name, but it was for the Back to My Mac service, where they have established a specific domain name just for this purpose. I mean that in using a similar method, they could, let's say, establish a domain name, and or the corresponding devices like Apple TV could use this domain name, not in order to be reachable, but just kind of for the certificate purposes.
Thank you.
Any other question? Okay.